for interview preparation. So in fluid dynamics, the important equation is Navier Stokes equation. This Navier Stokes equation is basically the governing equation for the motion of the fluid. So the equation considers the fluid to be incompressible, viscous, that means the viscosity is non-zero. So the three forces are required to equate to the inertia force. So the three forces which are necessary to make the fluid move or to overcome the inertia of the fluid are gravitational force, pressure force, and the kinetic energy force. Okay, so let's see what are the questions here. So this image of Navier Stokes equation. Let's note that. So if the viscous force is considered, what happens between the fluid particles? If the viscous force is there, that means the friction or the cohesive force between the particles is high. That means there will be shear stress among the fluid layers that is expressed as a viscosity. Okay, so how does it affect the fluid flow? So yeah, obviously if there is a viscosity present, that means there will be a velocity profile. That means the fluid layers are not moving at the same rate, at same momentum. So there can be energy loss due to that, which is expressed as a head loss there. So which law is considered here to express the viscous effect? So Newton's viscosity law is used here. So let's see what is it. So the fluid element in flow, they get viscous shear stress induced. So imagine this. I'll show you here. This is the flow with a pipe or something. So if this is the fluid element, imagine like this in a exaggerated way. So the fluid element is moving in this direction. So in this case, the the sides of this cube will face the shear drag stress, and the other two surfaces marked here will have a compressive pressure over these surfaces. That is why, as pressure is always compressive in nature, that is why there is a negative sign. So there are three forces which are acting on the fluid element: gravity force, pressure force, and the inertia kinetic energy force to move the inertia inside this fluid element. Okay, so yeah, so this is it, and this drag stress is expressed through the Newton's viscosity law, and the drag force or the drag force is expressed as drag stress times the area. Okay, so this three equation is basically the Navier-Stokes equation in three components: x, y, and z. So this first part is basically the gravitational force. This is the pressure force, and this is the kinetic force. And this whole expression is called inertia force. This first part of this curly ubicality is basically local acceleration, and all these three is basically convective acceleration. So this is the equation expressed like this. All these forces are expressed as a force by volume, right? Like this, it is expressed. So let's see what is written here. In which part of the fluid element drag stress acts? In which part of the fluid element stress acts? Is the fluid element in motion? Yes, obviously, and I have discussed these two equations earlier as well. So next is the equation LHS. What forces per volume are represented here? That is the gravitational force, pressure force, and the kinetic energy force, kinetic force. And RHS, how is the inertia force expressed? And which is local convective acceleration. So inertia force is expressed as mu times the this expression. And here is the local, and here is the convective section. How many components are considered in Navier Stokes equation? Three components: x, y, z. So pressure change versus pressure loss. We have discussed this already. Pressure change due to the as we discussed, it is due to the area pressure change, and pressure loss is due to the head loss. In how many ways the pressure difference be created? From the Bernoulli equation, how to find the pressure difference with respect to the friction head? How to tell the direction of the flow? So okay, from the Bernoulli equation, we have not discussed the direction flow part here. We just discussed how the head loss can show us the direction. So, and we have to also see how does the energy gradient line affect. So we will just see that and come back to uh, the Navier Stokes equation. So here from Bernoulli equation we have this expression which is equal to constant, and this first part is called physiometric head, and it's also called hydraulic gradient line, and this whole expression is the energy gradient line we have discussed earlier. And the difference between the energy gradient line and the hydraulic gradient line is v squared by 2g. So why do we use energy gradient line? So as we know, the difference between the two sections, the energy gradient line of this first section and second section, is due to the head loss, that is the viscosity or the friction in the pipe. And from this expression we have also derived that head loss is equal to P1 minus P2 by rho g, specific density. So the difference is used to tell in which direction the fluid will flow. If the energy is high here and less here like this, that means the flow direction is from 1 to 2. It is obvious, and this loss of energy is because of the head loss. And if the flow is uniform, that is what is written wrong. Uniform means the velocity doesn't change with respect to the position, and steady flow means it doesn't change with respect to the time. And in that case, the velocity at two sections are both same, and in that case, the difference between the EGL, HGL, energy gradient line, and hydraulic gradient line is v squared by 2g. In this case, the lines, both the lines will be parallel like this, and the difference will be v squared by 2g because this is the condition, v1 is equal to v2. If there is a sudden enlargement like this, that means the v2 is less than v1, in that case, the EGL and HGL line will be something like this because of the sudden enlargement. Okay, that is what is written here. So again, going to the Navier Stokes equation. So this is what we discussed, that how to find the direction of the flow through the EGL, HGL, and head loss. So now let's go ahead and discuss about the viscous flow. So what is viscous flow? Viscous flow is the flow in which the fluid has viscosity. The flow which contains viscous fluid or the surface has friction factor are called viscous flow. The viscosity is included with respect to the mu side. And this is the formula from Newton's viscosity law. So from this diagram you can see that this is the profile, velocity profile, and this is the shear stress profile. And this equation represents the velocity profile for the pipe flow. So this equation is representation for the parabolic profile. So you can see the difference with the capital R is the radius of the pipe, small r is the deviation from 0 to radius of the pipe. So drag stress is expressed from this formula, and the curly P by curly X is the change in pressure across the section is due to the viscosity of the fluid, and at particular section at this section there is a change in pressure. Okay, so due to viscosity there is change in velocity, and due to change in velocity there is change in pressure. At radius 0, that is at this point, the formula is something like this. The R is 0, so we get something formula like this, and at that point where R is 0, the shear stress is 0. At this point, shear stress is 0, you can see here. But at capital R, at the surface of the pipe, the velocity is 0. Okay, it gets cancelled, 0, but the shear stress is highest. Okay, so in this case we actually can say that the average velocity is maximum velocity by 2. So we will know how do we get this. Next is how to find the average velocity. Okay, this is how we will see. So this is the velocity profile, and let's take a small strip like this and find the area. So area will be the circumference times the thickness, that is dr. So for this area we can find the discharge, it is Q is equal to AV, and then from that we can find the discharge through this area, and for the whole pipe also by integrating it from 0 to R. After integrating we will get the velocity as something like this. as we know, the average velocity is equal to Q by area of the pipe. From this we can get that the average velocity is maximum velocity times divided by 2. So this from derivations. Then how to find the average velocity directly from the pitot tube? So we need to place the exactly at the radius position at which we can get the average velocity. From velocity profile equation we know that at radius 0 we have the maximum velocity, and at maximum velocity by divided by 2 we get the average velocity. Then we just have to use the velocity profile equations to equate it. So this is the maximum velocity profile equation divided by 2 is equal to the general velocity profile equation. So equating this we will get that the at radius 0.67 times the maximum radius of the pipe we get the average velocity of the fluid. Okay, if we have the average velocity of the fluid, then we can find the discharge of the whole pipe flow. So as written here, what are the conditions for the viscous flow? Viscous flow means it should contain viscosity or it should have friction in the pipe. Which law is prominent here? Newton's viscosity law. How much should be the Reynolds number for the laminar flow? So it is coming here. We will see that. So for laminar flow, the Reynolds number should be less than 2000. Drag stress with respect to the velocity gradient. So we will see that how does it relate with the drag stress versus velocity gradient later. So velocity profile for laminar flow, as we have seen, velocity change with respect to the pipe, we have seen that. Drag stress for the laminar flow, we have seen that. Change in pressure with respect to the section, yes, it changes. The pressure is high here, pressure is less here because of the viscosity, but it doesn't change at any section. Yes, obviously at particular section it doesn't change. Due to viscosity, velocity changes, thus the pressure changes. It is true. Then, how to find the average velocity? First we have to take the velocity section area, then find the discharge for the particular section, and then find the total discharge. And from that, if we divide the total area, we get the average velocity. To find the average velocity for a pitot tube, just use this relation, use the velocity profile, and then find the radius to find the average velocity at that point. So next we go to the turbulent flow in the pipe. So turbulent flow in pipe is also called eddies or mixed flow because of the eddies formed there. So in turbulent flow, the Reynolds number should be maximum more than 4000, and for the laminar flow, it should be less than 2000. So the profile, velocity profile of the turbulent flow is something like this. This profile is called logarithmic profile, and this small layer is called the laminar sublayer, and it has a linear profile. Turbulent flow basically contains a very small portion of a laminar flow. Okay, because this laminar flow is due to the friction or the viscosity of the pipe, which creates the boundary layer. We will see that later. Okay, so how much should the Reynolds number should be for turbulent flow? Does turbulent flow contain laminar flow? Obviously, viscosity profile in turbulent flow is logarithmic. Drag stress with respect to the gradient, velocity gradient, we will see that. So in turbulent flow, we also see about the Reynolds analysis. So Reynolds drag stress for the turbulent flow. Reynolds found the drag stress in the turbulent flow using this formula. This drag stress in turbulent flow is equal to viscous shear stress plus turbulent shear stress. Viscous shear stress is nothing by the Newton's viscosity law formula, but the turbulent shear stress is this formula, rho times fluctuating velocities at x and y direction. The velocity components can be found from Braden's formula. We will see that Braden is the student of Reynolds, and he found the fluctuating formula. So the famous thing about Reynolds is Braden mixing length. Mixing length means the length at which a lump of fluid elements travel to the other layer, such that the momentum at that layer in the fluid direction remains the same, and that length is called the mixing length. Okay. And the fluctuating velocities from the gradient is length, the mixing length times the velocity profile for the both U and V. From that we can get the turbulent shear stress as L times velocity profile whole square. So as it was asked earlier, what is the relation between the shear stress times the velocity profile? For laminar, the shear stress and the velocity profile are directly proportional. For the turbulent flow, shear stress and velocity profile are uh, directly proportional, but it is velocity square, velocity profile, velocity gradient times square. Okay, so mixing length. What is the mixing length of the lump of fluid elements? Fluctuating velocity and mixing length, we have seen that. Turbulent shear stress, mixing length, we have seen that. So next we will go to the head loss in the pipe flow. So how to identify the head loss in laminar as well as turbulent flow? So for laminar, we can use Huygens-Poiseuille equation. So he gave us the formula to find the head loss. HF is equal to P1 minus P2 divided by rho g, which is expressed as 32 mu u is the average velocity times the length by rho g t square. And Darcy equation, he gave a general formula for both laminar as well as turbulent, which is 4 times coefficient of friction F times length times u square by 2 gt. And coefficient of friction for laminar is 16 by R Reynolds number. The Reynolds number is less than 2000. And for turbulent is 0.0791 by Reynolds number times 1 by 4, power 1 by 4. Okay. So head loss is basically due to the viscosity as well as the friction. So two reasons for the head loss in the pipe flow: viscosity as well as friction. For laminar flow, are both the equations same? Obviously it is same. You will see that. So this is the Huygens equation, this is the Darcy equation, and these both are used for when the head loss is major. So for laminar flow, both the Huygens and Darcy equations are same. So you can see that from Darcy equation, this is general formula. When we put the coefficient of friction value 16 by Re, and Re is nothing but rho d u by mu. When you put this equation, you will get the Huygens equation for the lambda head loss for laminar flow. So in a given controlled volume, consider that the area is constant and the velocity is same at the sections here. That means this fluid element net force is 0. Okay. At this point, the forces acting on this element, net force acting on this element is 0. That means the pressure force as well as the shear force or the drag force are equal. That's why it is 0. So the pressure force will be changing pressure times the area, and the drag force will be stress times the area. Okay. And when we divide it with the rho g, we get such a formula, and from this coefficient of friction formula, we get again the Darcy equation. Okay, this is how we can derive the Darcy equation. Next is the head loss in pipe. There are two kind of head loss: major head loss, minor head loss. What we discussed earlier, the Huygens and the Darcy equation are basically for the head loss. So let's see what is written here for the control volume. In control volume inside the pipe, as we just said, area and stress are constant. Net force acting on the fluid is 0. Equal the forces, we get the using the coefficient of friction and the drag stress, we get the head loss formula. Okay. So major head loss are due to the friction and viscosity, and the minor head loss are due to the sudden contraction or expansion of the pipe, or bending, or the pipe fitting, or any other obstruction. And formulas for the head loss are basically derived from the empirical relation. Empirical relation is nothing but experiments are conducted, and from the data of the experiments we create a formula. And from that we find the head loss for this minor losses. So these are the minor losses: the sudden enlargement, sudden contraction. For this we can see that the head loss is changing velocity squared by 2g, and for this the head loss is half of the v squared by 2g. And in this situation, you can see that there is a sudden enlargement, sudden contraction here. That's why in this case, the head loss is half v squared by 2g. and for this sudden enlargement, it is called by 2G. Okay. So next is what is it here? Headloss formula. Obviously, Headloss formula here. So Headloss in series and parallel pipes. So series in parallel pipes, you can see that the flow is the discharge is same, but the head loss is added up H1 plus H2. But here the discharge, the Q3 is Q1 by Q2, but the head loss is same, H1 and H2 are same. And why join pipes in parallel? Because if we have a same power and we want high discharge from the fluid, then we have to connect it in the parallel combination. Why? Because for the same power, we get more discharge due to the less head loss. If we have a series, then we have a double head loss. The head loss get added. But if we have parallel, the head loss are reduced. Means we use less head loss compared to the series pipes. So what is water hammering? So water hammering is a situation at which happens in the reservoirs or dams. So the pressure wave generated in the pipe is due to the sudden closure of the valve here. So what happens is that when we suddenly stop the valve, the fluid is basically moving in certain velocity, and due to the sudden stoppage, there is a change in momentum of the flow of the fluid, which creates a force, opposite force, and that force is transmitted as a pressure wave in the pipe. Yeah. That pressure wave creates a sound, a hammering sound. That is the reason. And why there is a sudden stop in the water? Because we want to stop the turbine suddenly so that the electronic parts doesn't get damaged. Okay. So next we will see about the dimension analysis from the part of fluid dynamics for the integral preparation. So dimension analysis. So what are the basic fundamental dimensions? Those are mass, time, and length. And why do we need it? There are two reasons why we need the dimension analysis. The first one is to know if the formula is accurate. Second is if a phenomenon is dependent on some variable or it is a function of some variable, then the dimension analysis helps to form the formula. Okay. For example, let's say if some wrong formula is given, and we for some that kind of wrong formula, we won't be able to find the right dimensions. For example, the pressure formula is rho g q z. Sorry, the power formula is rho g q z, and if the power formula is written something like this, rho g by q z, so in this case we definitely won't find the required dimension of the power, right? So in this case it helps to check the formula or to develop a formula for the given phenomena. Okay. And next is there are methods of dimension analysis. There are two methods. One is the Reglish method, second is Buckingham pi theorem. So in Reglish method are basic method which is used for uh, dimension analysis in which we have maximum three variables, and we use Buckingham pi theorem method in this case for cases in which the phenomena contains more than three variables. Okay, for interview purpose, this is more than enough to know about these methods. So let's move on to the modeling analysis, which is used in dimensional analysis. So what is a model? Model is nothing but a replica of actual prototype. So this replica can be smaller, larger, or same size, but it must be similar. The keyword is similar to the prototype. What kind of similarity can it have? It must have geometric similarity. That means the dimensions should be in particular ratios with respect to the actual prototype. Second similarity should be kinematic similarity. That means the velocity acceleration should be in similar ratio. Same with the third important thing is the dynamic similarity. That means the forces, gravitational force, inertia force, pressure force should be similar. Okay, and why do we use it? Why do we need modeling analysis? Because it reduces the resource wastage. Because for example, let's say if you want to analyze a dam, so we can't afford to analyze the real dam. We don't want to build a real dam and then analyze. So what we do is create a smaller version of it and find and build the prototype, build the replica of the model in such a way that it resembles the actual dam. Okay, so in this important similarities, dynamic similarity, which we are more concerned about, is the dynamic similarity. To compare dynamic similarity, forces are to be compared. Okay, so we shouldn't directly compare the replica or the model's force and the actual force, but we need to take the ratios. So for that we use, or we compare using the dimensionless number. Okay, so these are basically ratios. So let's see what are these dimensionless numbers. So in dimensionless numbers, there are basically five dimensionless numbers. First one is Reynolds number, Froude's number, Euler's number, Weber's number, and Mach number. So Reynolds number, as we know that Re is equal to Vd by kinematic viscosity, and this is nothing but the ratio of the inertia force divided by the viscous force, as we know that. And this Reynolds number is used only for those cases in which it is a pipe flow or it is a fully submerged flow. And next dimensionless number is Freud's number. This is Freud's number. Fe is equal to root of Fi by Fg, that is root by the ratio of inertial force divided by the gravitational force. And the Freud's number equation is V by root 2g. And these Freud's number are used for open channel flow, in which we have atmospheric pressure over the flow of the fluid. And the third one is the Euler's number, which is the ratio between the inertial force divided by the pressure force. And these are basically used in the cavitation situations. You will see that what is cavitation next. And next one is the Weber number. It is the ratio of inertial force divided by the surface tension force. Third one is Mach number. Mach number is a ratio of root of inertial force over the elastic force. And as we know that the Mach number is nothing but the velocity of the body divided by the sonic velocity. That is a velocity of the sound, speed of the sound. And these are used where in some cases like water hammering or torpedoes or any high moving bodies, high speed bodies. Okay, so that's what written here. What forces are compared? As we know, inertial force and viscous force. In which condition are they used? They are used for fully submerged case. And Freud's number. Which forces are used here? Inertial force by the gravitational force, and the conditions are it is the open channel case. Euler's number. What forces are used here? Inertial force as well as pressure force, and they are used for cavitations. We will see about the cavitation next. Weber's number is the inertial force divided by the surface tension force, and used for the capillary conditions. Mach number is ratio between the surface inertial force divided by the elastic force, and you know the Mach speed formula, and in which condition they are used for high speed bodies. Okay, so let's see what is cavitation and how does the cavitation happens in the fluid flow. So let's say in this venturimeter, I would say there's a nozzle here which has converging part, throat, and diverging part. In this case, the rotation area increases the velocity here as well as the pressure reduces here. As we know that area is directly proportional to the pressure, and velocity is inversely proportional to the area. So it means whenever the area decreases, the velocity increases as well as the pressure decreases. So in this case, as we know that every fluid has certain vapor pressure. Vapor pressure is the property of the particular fluid. So at is a constant vapor pressure. It's a constant. And for boiling condition, two things to make the fluid boil. There can be two conditions. One is when the pressure is constant. At that point, we are increasing temperature. Then the boiling can happen. Okay. Second thing is that we have a constant temperature, but the pressure is decreased. At that case, also the boiling can happen. Okay. So what happens in this throat area is that when the pressure decreases, the boiling happens. Okay. As the pressure decreases, when it decreases less than the vapor pressure, then the boiling happens. So when the boiling happens, the bubbles are created and they burst on the surface of the diverging part. So when they create pitting effect, like tap, so, pittings here in the surface, and that creates cavity on the surface, small holes, and due to that cavity, it can create eddies, and that eddies creates loss of energy or head loss in the flow. So next is let's talk about the boundary layer. So boundary layer is an important topic in uh, fluid dynamics. Okay, so let's see what are the points here in boundary layer. So from this picture you can see that here as well as here, this line represents the boundary layer. So let's say at a given section here, in this section of the flow, two sections, let's say the flow starts from here at this point, and it has a free stream velocity u alpha, and when it passes through the surface, let's say it is a plate here, flat plate, and as we know that for laminar flow the Reynolds number for the flat plate should be less than 3 lakhs, and for turbulent flow the Reynolds number should be more than 5 lakhs. So for a flat plate, the fluid is moving like this, and here is the friction on the plate. So due to the friction as well as the viscosity of the fluid, what happens is that it creates the velocity profile, parabolic velocity profile is created. And due to the friction as well as the viscosity, there is a line which can be drawn like this. This line, this area, basically represents that the velocity of the fluid in this area is less than the free stream. We will know uh, uh, we will know the reasons behind that later. But for now, we can say that in this layer, this boundary layer, the velocity of the fluid is less than the free stream velocity, and the reasons are because of the friction of the plate as well as the viscosity. So which creates this layer. Okay, and from this layer, we can see that at this point the shear stress is maximum. That is why the velocity gradient, this velocity gradient is zero at this point. Velocity gradient is nothing but the slope of this parabolic curve. So until this point, the slope is there is a very high slope. That is why the um, velocity velocity gradient is high until this point. After this point, the velocity gradient is zero because the slope is zero. That is why there is no shear stress or drag stress after this boundary layer. That means after this boundary layer, the velocity gradient is zero as well as shear is zero. That means the fluids flowing through above this layer have the free stream velocity. Okay, and as this fluid moves at certain distance, after that the fluid gains inertia. Sorry, the inertia as well as the boundary layer also decreases. Due to that, mixing happens. The fluid element mixing happens. Due to the mixing, the flow becomes turbulent, as well as the flow can also become turbulent when the velocity also increases. And velocity increases because the inertia inside the body is less than the kinematic energy of the flowing fluid. So due to that, the flow becomes turbulent. Okay. So what can we say about the when about the stuffs below the boundary layer? So below the boundary layer, the velocity gradient is non-zero. That means also the viscosity is not zero. Viscosity is not zero in any of the cases. Some say that in this boundary layer, inside the boundary layer, the viscosity is there, and outside the viscosity not there. No, viscosity is always there. Viscosity is a property of the fluid, so it is always there, irrelevant of the friction of the body or the boundary layer. Okay, and below the boundary layer, the stress is non-zero, and the boundary thickness is a distance till which the velocity gradient exists. Uh, this is called boundary thickness at a particular section, and the velocity is less than the free stream velocity. And above the boundary layer, the velocity gradient is zero, stress is zero, the flow is equal to the free stream velocity. Okay, so the same thing is explained here. We just discussed all these things. So next is boundary layer, is it a real boundary? So okay, this is not the real boundary we can say. This is an factual, this is an hypothetical assumption that this boundary is created because this boundary lets us know to study about the losses happening in the flow. So that is why we study boundary layer, to study the losses. All the drag force losses are absorbed in this thin boundary layer. More than 90% of the losses are studied inside the boundary layer. We don't need to go outside the boundary layer. So that is why the boundary layer analysis is most significant. So when the losses are calculated, we can know about the pumping power. So if we know what kind of losses are happening in this boundary layer, we can judge how much is the discharge, how much the power should be supplied to create to generate the necessary discharge. So as we know that to this boundary layer, the velocity profiles are created. So for the laminar, it is a parabolic profile in which the velocity is directly proportional to the y square, that is the y direction. And for the turbulent flow, it is a logarithmic profile, and the velocity is directly proportional to the y direction power n, and n is the value is called power law. N is equal to 1 by 7. And as we know, the Reynolds number as velocity times the distance by the kinematic viscosity. Whenever the distance increases, the Reynolds number increases. Okay, so there are three properties which decides the Reynolds number, as we have discussed earlier itself. So that's it till this point we have discussed it. So let's talk about the boundary layer thickness. So what is the distance with respect to the velocity? Why 99% of the free stream is considered? Okay, let's see. So boundary layer, as we discussed earlier, the boundary thickness is this distance for the particular section. And what is that distance? How do we get it? That distance in the transverse direction, that is in y direction, at which the velocity is 99% of the free stream velocity. If you just move above and measure the velocity at this section, at that particular point where the velocity is 99% of the free stream velocity, at that distance is called the boundary thickness distance. Okay, at the particular section. Okay, and why do we need 99%? To get 100%, the 19% can be reached here, but to get the 100%, we have to move above, and we don't need to do that because uh, the boundary layer range will be much more if you want to find the 100%, and it doesn't make much sense as its effect is negligible when we go to 100%. Only 19% is enough, and majority of the effects are noticed within these boundary layers, within this 19%. So majority of the losses on the effects on everything can be measured between in this 19% of the free stream velocity, and this distance is called the boundary thickness. Okay, so next is the loss due to the boundary layer formation. So what are the three losses due to the boundary layer formation? How are the three losses calculated with respect to the thickness? We will see that. So losses due to the boundary layer formation. So below the boundary layer, the velocity is reduced less than the free stream velocity due to the inertia of the fluid, or inertia of the fluid, which happens due to because of the cohesive force inside the fluid, and which is also described as the viscosity, and also the resisting force or the friction force on the plate. So this creates a total overall inertia force which resists the body from flowing. So due to this reduction in the velocity inside the boundary layer, three things happens. Three things gets reduced. First thing is the discharge. Discharge is less because the velocity is less. Second thing is the momentum is reduced because the velocity is reduced. Third thing is the kinetic energy, that is half mv square, because of the reduction in the velocity. All these things are lost, and these are calculated as three thickness terms. So the first thickness term is the displacement thickness layer. So this indicates the loss of discharge due to the formation of the boundary layer, and the formula is expressed like this. In this case, the velocity is the function of transverse direction y, and the relation between the transverse direction and the thickness is related like this: u by free stream velocity whole square. If, let's say, in a given problem, the displacement thickness layer is given, then discharge is to be calculated. We can calculate it like this: the discharge is equal to velocity times the area, and the area is nothing but the uh, boundary thickness times the uh, width of the plate. So this area is used for the discharge. So when we know the free stream velocity as well as this area, we can calculate the discharge. And from this discharge, we can also calculate the mass flow rate. Mass flow rate is nothing but discharge times the density. We can find the mass flow rate here. So next is the momentum thickness. Momentum thickness shows the loss in the momentum, and the formula is expressed like this. And next one is the kinetic energy thickness, which expresses the loss of kinetic energy through boundary layer thickness. So this is the formula. Okay, so we don't need to know it, but just to know that the loss of these three, discharge, momentum, as well as kinetic energy, are expressed through the boundary layer thickness with respective terms. That's it. So let's move on to the drag force and coefficient of drag. So what happens is that if you take a plate like this, there's a friction here. At this point, the shear stress is high, as well as there's a shear stress is high, that means the drag force will also be high at this point. So what is the drag force? Drag force is nothing but the shear stress times the area, that is width times the thickness dx. This can also be expressed as CD times half rho u square times a, is evaluated from the formulas. Okay, so the CD is nothing but the coefficient of drag, which is equal to actual drag force by the theoretical drag force, which is Ft by this half mu a square. And there's another term, C star D, which is basically local coefficient of drag, which is the actual drag stress by the theoretical drag stress. And next is Bollich's velocity profile. So in some cases, when we don't know the velocity profile, we generally take the velocity profile. For laminar profile, we take parabolic velocity profile, in which velocity is directly proportional to the y square. And in those cases, the displacement, the boundary layer thickness is expressed like this, as well as the coefficient of drag is expressed like this. For turbulent, we use the power law of 1 by n is equal to 1 by 7, and for the boundary layer thickness as well as the coefficient of drag is expressed like this. Okay, and when we take the Reynolds number, we take for the boundary layer thickness, we take this x distance. For the pipe, we take the diameter, but for the uh, boundary layer thickness, we usually take the length of the pipe, length of the plate or the pipe, okay, to calculate it. But for the coefficient of drag, we use the diameter. Okay, so what is the relation between the boundary layer thickness as well as the distance? So let's say for the laminar case, the boundary layer thickness is expressed like this in this formula. That means the boundary layer thickness is directly proportional to the root of x from this derivation, directly proportional. As far as for the turbulent, the boundary layer thickness is proportional to the x power 0.8. Okay, so these are just observations. So let's know, is the boundary layer good or bad? So it basically depends upon the applications. So it is basically bad in the case when we want to prevent the heat transfer, because it prevents the heat transfer. For example, let's say if you want like an engine or a computer or capacitor which contains a wing kind of plates to reduce the heat. That means a part is heating part is here and the plates are attached here, so that the heat can transfer through the plate and the heat can just dissipate by using the convection radiation to convection process. The heat is released outside. What happens is that if the flow is happening like this over the plate, due to the boundary layer, the heat doesn't get transferred outside because of this boundary layer. That means it reduces the heat transferring effect. But it is good because it protects the surface from erosions. Okay, it is good at that particular case. So next one is the boundary layer separation. So what keeps the boundary layer stick to the surface? How does the inertia builds up inside the boundary layer? How does boundary layer separate and how? So when does the boundary layer separate and how does it? So Energy in the free stream, that is the kinetic energy, yeah, half a wave square, keeps the boundary layer stick to the surface. But after some time, the distance they break. Why? The inertia in the boundary layer fluid is due to the friction and the viscosity, as they are not moving with the same velocity. Okay, that's true. The friction of the blade as well as the viscosity, they creates the resisting force of the free stream velocity. That's why the velocity is less inside the boundary layer. So inertia keeps increasing as the incoming stream force speed increases, and at some point the incoming free stream energy is not sufficient to keep the boundary layer. So as the inertia builds up, so a lump of when the inertia builds up high, very high, at some distance, a lump of fluid element mixes with the free stream in other layer, creating eddies. And this is bad as it reduces the energy flow in the as it reduces the energy in the flow. Okay, so that's why it gets separated. So next one is the adverse pressure gradient, one of the reason for boundary separation. So what happens is that when the fluid is transferring through the nozzle, which it has converging throat and diverging parts. So what happens is that when the fluid is entering here, the pressure is high here and it's less here. So fluid transfers. As there is high pressure, that means the velocity is going to be high inside. So what happens is that it creates a parabolic profile and it creates the boundary layer here. Okay. So when it passes through and comes outside, the velocity is increased and the pressure is high, area is high. What happens is that velocity is low here because it's coming outside. Pressure is high. What happens is that the velocity profile converts here like this, negative to positive. So pressure is high, the velocity gradient is negative here, as you can see. Due to the gradient velocity, the it creates a turbulence here, creates eddies. You will see that. So less pressure gradient here. So outside the pressure is high. So the boundary layer sticks to the bottom. The kinetic energy of the free stream increases due to the free stream increases because the pressure is less. So kinetic energy increases. That's why the velocity also increases here. So here in this case the pressure is increased. So the kinetic energy is less. Kinetic energy less because it's a larger area. So kinetic energy will be less, obviously. So in this case the boundary layer separation happens because the high pressure and low velocity gradient. Okay. So boundary layer separation always is bad because it leads to the mixing or it creates eddies, which creates ultimately the losses, energy losses. So it is good when the pressure gradient is less than 0 and the velocity gradient is more than 0. It is less, it is bad, or the boundary layer separation happens when the pressure gradient is greater than 0 and the velocity gradient is less than 0. Okay. So that is the reason we have seen the reasons why it is good or bad. It's always bad basically. And the next last thing is the nozzle design. So how, if you want to design a nozzle, how do you want how do we want it to be? So do we want the converging part to be lengthier or narrow, or throat to be narrow, or the diverging part to be narrow? So we always want the diverging part to be narrow or lengthier, because if you have a sudden increase in the area, it creates uh, high pressure as well as negative velocity gradient. If you have a narrow tube, a narrow lengthier tube, there will be a gradual increase in the pressure. That means it will create less eddies. That means less loss. So we don't want sudden increase in the diverging part. Neither we want the long part, because long paths are not efficient as well as economical. Okay, so that is the reason we don't want a lengthier part. We just want like this. The converging part can be shorter, but the diverging part has to be bigger to reduce the eddies. Okay, so that's all for this fluid dynamics. We will next see about the fluid machines. Thank you.